So in this segment, we will see the details of Dijkstra's algorithm and see the reason why it's correct as well. So here's the pseudocode for Dijkstra's algorithm for the single source shortest path problem. The algorithm takes three arguments. So it takes the graph, a weight function on the edges, and the source vertex from which we want to find the shortest paths to every other vertex. So initially, recall that capital S is the set of vertices for which we know the shortest path. So we initialize capital S to just the source vertex because it's the only vertex for which we know the shortest path. And we set the distance to S to be 0 because there is a shortest path of distance 0, of total distance 0 from S to itself. Then we also initialize the distances to the other vertices. For vertices that are in the neighborhood of S, we initialize the distance to that vertex U to be just the weight of the edge from S to U. So if there's a single edge going from S to some vertex U, we can set d of U to be the weight of that edge. But if there is no such edge going to a vertex U, we set d of U to be infinity, and for practical purposes, you can set it to be a really large number. But basically infinity is just some number much larger than any other number that arises in the problem. So that's how the d values are initialized. And then Dijkstra's algorithm repeats this while loop until all the vertices are brought into capital S. Initially, capital S is just little s. Which vertex does it bring into capital S at any stage? It picks the vertex U, which is the argmin of d of v. In other words, it picks the vertex U that has the least value of d of u over all the vertices which are on the other side in v minus s. So it picks that vertex U and brings it into the source side, capital S. Now, once it's brought U into the source side, here's capital S at any given point, and say U is the vertex that's brought in. Once it's brought U into the source side, for any vertex on this side, this is v minus s, now I can stop for a minute and tell you what, for a vertex v here, what does d of v mean? D of v is going to be the length of the shortest path from the source that stays entirely within the capital S side and then takes one single edge over to the other side. D of v is the length of such a path. So what are the possibilities? After you've brought U over to the source side, there are two possibilities. There was already a shortest path of that kind going through from S and then jumping over to V. There was one shortest path, and that's what we were maintaining in D of V. But maybe now that U is on the source side, there's an additional possibility for getting to V. That may be to take the shortest path to U from the source and then jump over to V. So you've got to compare which of these two is a shorter path to V that stays entirely with the source side and then jumps over to V. And this line of pseudocode, d of v, is the minimum of the old d of v, which was the length of the shortest path that passed through S and went to V before U was put into S. That's the old possibility. And the new possibility is you take the shortest path from the source to U, followed by the single edge of weight uv, if one exists. So for each neighbor v of u, you've got to make this adjustment. D of v may go down because it's from its old value if the minimum happens to be the second term here. Otherwise, d of v stays what it was. So this maintains the property that d of w is the length of the S to W path, there should be W here, the S to W path going only through vertices in S. So again, D is always going to be a value, D of any vertex is going to be a value of the length of the shortest path that goes only through capital S before jumping over to that vertex. So why does this algorithm work? Again, it's an algorithm that's complicated enough that you would need a proof to believe that it works. I would hope so, because it's not at all clear that we haven't missed some shorter paths along the way, or we have ignored some case. So here are some ideas behind the proof. So first, let's prove a very simple thing. For any vertex v, d of v can change over the course of the algorithm, but the change is always downward. That is, d of v cannot increase as the algorithm progresses. Why is that? That fact is easy to see because you look at the pseudocode and see where is d of v being adjusted. There's only one line where d of v is being adjusted, and it's being set to the minimum of its previous value and some new term. So if it's going to be the minimum of the previous value and some new term, it cannot be higher than the previous value. So d of v does not increase as the algorithm progresses. Second lemma, if u is brought into S before v, then d of v is greater than or equal to d of u. So this is saying that as the vertices we bring into S are ordered in terms of their distance from the source. The first vertex we bring into S is the vertex that's closest to the source, then the vertex that's second closest to the source, the third closest to the source, and so on. That order is maintained throughout the algorithm. Why is that? Here's the proof by contradiction. I'll let you read the proof for yourself, but I'll draw you a picture to illustrate this proof. So here is the source vertex S. Suppose for contradiction that d of v is actually less than d of u, but v was brought in later. So here is u, and here's vertex u, and here's the shortest path to u, whose length is d of u. This is d of u. And here's the vertex v, which was brought in later, but it's assuming for contradiction that this path is of shorter length than d of u. So d of v is less than d of u is what we are assuming here. So if this happens, along this path, let w be the first vertex on the path brought in after u. So u was brought in at some point. Let's look at the first vertex on the path from S to v that was brought in after u. That vertex could be v itself, but it's some vertex. But we know that d of w is less than d of v, because recall that these edge weights are all positive. So d of w is, say, less than d of v. They're positive, or at most d of v. They're non-negative. So d of w is less than d of v, which is less than d of u. But if d of w is less than d of u, then why didn't we bring in w instead of u? Recall that the algorithm works by bringing in the vertex which has the smallest d value at any point. So the vertex just before w on this path, whatever it is, call it x, was already brought in before u, because w is the first vertex brought in after u. Because x was brought in, d of w was already the correct value. The value d of w was already fixed. And it was smaller than d of u. If that's the case, w should have been brought in before u according to the algorithm. So this can never happen. So we have a contradiction, which means that d of v must be greater than or equal to d of u. So now for the main theorem that proves the correctness of the algorithm. At all points in the algorithm, the following are true. The following invariants are true for the algorithm. And this is, by the way, a standard method for proving an algorithm correct. You show that certain invariant properties are true from iteration to iteration, and then if they hold at the very end, that immediately implies that the algorithm is correct. So this is a style of proof that we are illustrating in this one example. For any vertex v on the source side, d of v is going to be the length of the shortest path from S to v with no qualifiers, meaning is the absolute best shortest path from S to v. For any vertex v on the source side, d of v has that value in it already. So no more changes to d of v. We'll never discover a shorter path to v. The second invariant is for any vertex v that's not on the source side, and I've shown this picture a few times. I'll draw it again. Here's the source side, and then here's the non-source side. And we're saying for any vertex v that's not on the source side, d of v represents the length of the shortest path from S. So for any vertex v on the v minus S side, d of v represents the length of the shortest path that wanders around S and then jumps over to v, as we've said before. So that's what's embodied in the second invariant. For any vertex v in v minus S, that's like this v, d of v is the minimum length of an S to v path with intermediate vertices only in capital S. Meaning you're not allowed to wander around on this side, on the v minus S side. You can only wander around on the S side. How do you prove a theorem like this? And this is a theorem that's supposed to apply at every point in the algorithm as the capital S set keeps on varying. You prove it by induction on the number of iterations, these invariants. So you prove that these things hold in the beginning of the algorithm, then assume they hold after a certain number of iterations, and prove that they hold after the next iteration. Okay, so initially what do we know? Initially, capital S is just the singleton set little s. D of S equal to 0, which is the length of the shortest path from S to S. The only paths with all intermediate vertices in capital S, remember capital S consists of one vertex, little s. So any path from little s with all intermediate vertices in capital S must use only one edge and get straight to its endpoint, its destination. So the only paths with all intermediate vertices in capital S are exactly the length 1 paths for which D of U is set correctly. What's a length 1 path? It's an edge from S to a neighbor of S. And for any neighbor U of S, we've set D of U to be the weight of the edge SU. For all other vertices that are not neighbors of S, there are no such paths, and so D of U equals infinity. So initially, these two invariants hold that are stated in the theorem, and now let's see why these hold later on. So assume these invariants are true just before bringing little v into capital S. What happens after we bring little v into capital S? So the proof now hinges on showing that these invariants hold after we've brought v into capital S. So when we bring v into capital S, d of v is the length of the shortest path to v. Why is that? Because let's see the picture again. So here's capital S. We just brought in v from the other side. And here's v minus s. We've already found d of v already is the shortest path now that stays entirely within S. Could there be a shorter path to v that actually goes out of S to v minus s and then comes back? Note that any path that goes out of S to some vertex u in v minus s must pay at least d of u to get to u. That's the invariant we've maintained so far. But d of u is greater than or equal to d of v, because we brought in the vertex which had the minimum d value. So any path that tries to go off into v minus s to some vertex u and then come back to v is going to be longer. So in fact, this proves the first statement in the invariant that d of v is in fact the length of the shortest path from S to v, no conditions. For any vertex u in v minus s, either the shortest path to u or with all intermediate vertices in S passes through v, or it doesn't. If it doesn't, then we already have its length in d of u. If it does, its length is d of v plus w u v. So let me illustrate that also. So if you take any vertex u, the shortest path from S to u, and we just brought in v into this side. Just remember that v is the vertex we just brought in. The shortest path staying entirely within capital S and then going over to u either goes through v or it doesn't go through v. If it doesn't go through v, we already have that length in d of u. D of u is the length of such a shortest path. If it goes through v, then the length of such a path is the shortest path from S to v, which is d of v, plus the weight of the edge from v to u, which is weight of uv. It should be weight of vu. Weight of vu. Okay. So again, since our update did exactly this, for every vertex u in v minus s, we checked to see if d of v was, the original d of v was smaller, or d of u was smaller, or d of v plus weight of vu was smaller, and we updated d of u accordingly. So again, d of u is correct, and the invariant holds after v is brought into the S side. So this is why the algorithm works, because if this invariant continues to hold as vertices are coming into capital S, at the end, all the vertices would be in capital S, and the first invariant says that the d values of the vertices are in fact the lengths of the shortest paths to those vertices. So we've found the shortest paths. The theorem in the previous slide ensures that Dijkstra's algorithm is correct, and we are finding the lengths of all the shortest paths. Now, all of this is just an algorithm to compute the lengths of the shortest paths to every vertex. If you did a little bookkeeping, you can actually compute the paths themselves. How do you do that? Whenever we change d of v or d of u because some vertex v was brought onto the source side, we update something like the parent of u to be v. We always remember which vertex is causing the current value of d of u. So for any vertex u on the v minus s side, here's the s side, we keep track of which vertex v is causing the current value of d of u. And if we keep track of these parents, then we can actually figure out the shortest path. The shortest path finishes by, actually the shortest path to u is the shortest path to the parent of u, followed by the single edge from the parent to u. So what is the running time of Dijkstra? And while we talk about the running time of Dijkstra, this also applies to the running time of Prim's algorithm, which we did not analyze for running time in the previous week. So, well, the running time of Dijkstra's algorithm depends very much on how you keep the values d of v. We could keep all the d of v values in an array indexed by the vertex. So that means that this is an array of size n. At every stage, when we want to bring a vertex into capital S, we have to find out what is the minimum value in this array. And that can involve searching through the entire array that can take order n operations per round. There are n rounds in all because you have to bring in n vertices. So that's a total of n squared. Now, every time we bring in a vertex to the source side, we have to update the d values for all the neighbors of that vertex. But that's only one update per edge. And the total number of edges is m, so that's order m updates, and m is never more than n squared. This is also order n squared. So the overall running time of Dijkstra's algorithm, if we represent d using an array, is order n squared. The alternative is we could keep the d values in a heap, because notice that one of the things we want to do is to find the minimum d at every point, the vertex with the minimum d value at every point. This would be ideal for a min heap to do because we can extract the minimum. But once we get the minimum value, we may have to update some d values. So we may need to do extract min n times. For each round, we'll need to extract the vertex with the minimum d value. And that takes order n log n because each extract min takes log n time. And now we also need to update, for every edge, we need to update the d value of the other end, as we said earlier. And an update in a heap can simply be done by deleting a key and then inserting it back with a new value. And that also takes log n. So the number of updates is m log n, which is the number of, m is the number of edges again. So the total running time of the algorithm is dominated by that second step. M log n is always at least as much as n log n in a connected graph. So, so the two options are to use an array and get order n squared, or to use a heap and get order m log n. They're both possible implementations of Dijkstra. Which one is better? Well, that depends on whether the graph is dense or sparse. So density and sparsity of a graph relate to the number of edges the graph has. The graph has close to n squared edges, then it's said to be dense. On the other hand, if it has close to n edges, or a little over n edges, then it's said to be sparse, and in between, you can, depending on the context, you can choose to call it sparse as well. So, so if the graph is dense, that is, it has about n squared edges, m equals n squared, then which is better? Well, it seems that the array implementation is better. It should be in order. Array implementation is better. Whereas if the graph is sparse, meaning it has m is quite a bit smaller than n squared, then the heap implementation might be better. So the choice of which implementation to do depends on how dense the graph is. Now finally, does Dijkstra's algorithm work with what happens with negative weights? Does it work or does it not work? Here's an example to show why it doesn't work. So if you look at this graph, there's a negative weight edge of length -3. So the algorithm will start out again finding that neighbor of S that has the smallest weight edge, and that's A. And so it'll bring little a to the source side and fix its distance to be 2. But that's incorrect because, in fact, the shortest path to A can go through B and come to A, and that has a total cost of 1. So the argument we made earlier was that there couldn't, if you have SA is 2 is the smallest weight edge from S, you couldn't get a better path going somewhere else because all weights are positive. That argument no longer holds if weights can be negative. You might take a longer first edge, but make up for it by a negative second edge. So Dijkstra's algorithm does not work when edge weights are negative.